Rhoades, coming from UC San Diego. We're very excited to have him tell us about characters of local permutation statistics.
All right. Well, thank you very much, Oliver. And as the last speaker, I just like to thank the organizers for putting on an absolutely terrific conference and for inviting me to speak in it. I'm also really looking forward to these posters. Thank all of you. I thank all of you for coming. I see some of you are coming from a very distant time zones where it's really kind of an odd hour of the night. So I'm really honored that you came to this talk. And maybe the poster session afterwards is even crazier, but I am sure it will be amazing. So what I'll be speaking about today is joint with Zach Hamaker at the University of Florida. So let's see here. So we're going to be talking about permutations. And of course, this has made an appearance in multiple talks so far, and in particular, permutation statistics. So this is kind of a very massive subject within our field, algebraic combinatorics. And I want to kind of isolate an interesting class of permutation statistics that Zach and I call local. So they satisfy some notion of locality. And after talking about local permutation statistics, I'll talk about local class functions. And of course, class functions are even more awesome than statistics because we have this very powerful artillery of symmetric functions we can apply to them, and we will. And we'll talk about some applications of our theory to pattern enumeration, so patterns and permutations. And this will generalize some very beautiful work of Chris Gates and Chris Reba. And then we'll get into the proofs. So the proofs are actually going to be, well, at least in my view, kind of interesting. We're going to learn something new about the character theory of the symmetric group. It's kind of cool when that happens. And this new information will take the form of this thing that I call the path Murnaghan-Nakayama rule. So we're going to have somehow a new combinatorics of ribbon tableau that's going to show up. So let's get started. Permutation statistic, I'm going to take a kind of a vanilla definition here. It's nothing more than a real valued function on the symmetric group. And we've seen these, we teach these to our students. Here are some famous ones. The exceedance number of a permutation, it's the number of points I at which your permutation exceeds expectations, for which W of I is bigger than I. You have the inversion number, that's counting out of order pairs. You have the descent number, an Eulerian statistic that counts out of order pairs that are kind of right up next to each other. You have the major index, which is a kind of weighted version of this descent statistic. You sum up over all descents, Wi bigger than Wi plus 1, and you add up the position of that descent. And then another important statistic, just the number of cycles and the cycle decomposition of a permutation. So we've seen these guys before. And I want to assert a kind of dichotomy in this picture. Like one of these things is not like the other sort of thing. And here's the intuition for this dichotomy. So a statistic, F, from the symmetric group to the real numbers, roughly speaking, is going to be K local if you can compute F by restricting to K element subsets of the integers between 1 and n. Like if I compute exceedances, I just have to look at one entry at a time. If I compute any of inversion, descents, or major index, I'm just looking at pairs of entries and kind of adding something up. But if I want to look at number of cycles, well, that's really more of a global thing, right? If I want to see what's a cycle in a permutation, if you just show me a bit of a permutation at a time, I just have to kind of, march around and somehow it's behaving differently. So this is a intuition for a definition that will make more formal in just a little bit. So what does locality mean? This is not advancing for some reason. There we go. So our notion of locality comes from something that we're terming partial permutation. So a partial permutation of the integers between 1 and n having size k is just a bijection between two subsets of the numbers between 1 and n, s and t, where those sets both have size k, right? So it's partial information of a permutation. And I'm going to let S and K denote the family of all partial permutations of n of size k. So how can we write partial permutations? Well, inside S52, here's sort of a partially defined bijection from the numbers between 1 through 5 to that same set. And we can write this in something like two-line notation, which would usually be a two-row matrix, but I'll just kind of write the rows next to each other. So I have one list of numbers 2, 3, that list has size 2, and another list of numbers 5, 1, that list also has size 2. Right? So these are ways of writing partial permutations. And given a partial permutation, we have a very simple statistic on the symmetric group, namely an indicator statistic, which I'm writing boldface 1 ij. And what does this statistic do? Well, it basically measures whether a given genuine permutation is compatible with a partial permutation. So 1ij evaluated on a permutation W is going to be 1 if W sends the ordered list I to the ordered list J and 0 otherwise, right? So for every partial permutation, we have this indicator statistic. And this leads us to our definition of locality, right? So this isn't going back and forward for some reason, but okay, here we go. So a permutation statistic F is said to be k-local if there are some numbers, Cij, in the reals, such that if I sum up over, sorry, this is kind of small, all size k partial permutations in Sn, it's the same k, of the corresponding linear combination of indicator functions, I recover the statistic in question. So the 16 statistic is one local, right? Just depends on one entry at a time. Inversions, descents, major index, those are all two locals. They depend on pairs. And number of cycles, well, that exhibits no non-trivial locality, right? So this is what local means for these classical statistics that show up all the time for us. So what do I mean by no non-trivial locality? So how do I get this to advance? Here we go. So the basic idea here is that the locality of a permutation statistic should be thought of something analogous to polynomial degree, right? So a k-local statistic is a little bit like a polynomial, which has degree at most k. So for example, the 0 local statistics are nothing more than constant functions on the symmetric group. A k-local statistic is also k plus 1 local, you can check that. And actually any statistic is not just n local, but in fact n minus 1 local. So we have this kind of nested family of increasing complexity, if you will, of permutation statistics. And all right, are there any nice 3 local statistics like peak, for example? Peak is a 3 local statistic, or left peak or right peak, things like that. So what else can we say about locality? What else does it have in common with polynomial degree? Well, a linear combination of k-local statistics remains k-local. And also, if you have a k-local statistic and an l-local statistic, you can pointwise multiply them together. And what you get is something k plus l local. Right, so there's a... Sorry, I'm having issues with advancing all of a sudden. So you might also be kind of interested in a more algebraic way to look at what locality actually means. And that comes from something which is often called in the literature the Fourier transform. I admit I prefer algebra over analysis, so I'm calling it the Artin-Wedderburn theorem, but it's essentially the same thing. So the Artin-Wedderburn theorem says that we have a certain isomorphism of algebras. And this is usually stated for finite groups over the complex numbers, but the symmetric group is just so nice and well-behaved, I can state it over the reals. We have an isomorphism from the symmetric group algebra, R brackets Sn, to the direct sum over all partitions of n of, well, the real endomorphism space of the corresponding Sn erep, right, V lambda. And how does this isomorphism work? Well, if I have a symmetric group algebra element that acts naturally on any module over the symmetric group, and I just take the direct sum of the corresponding linear transformations. And the Artin-Wedderburn theorem says that this is an isomorphism. And there's this result that I just called ubiquitous. I have not been able to find the origin of this. It seems to keep getting proven and reproven, and parts of it are proven, or equivalent versions of it are proven throughout the literature by many different people. Ellis, Friedgut, Pipel, they were working in extremal combinatorics, even Zohar, that was a probabilistic combinatorics. Wang, Gersht, and Gibas, that was actually machine learning, believe it or not. So they have this more intrinsic definition of what it might mean to be k-local. So a statistic f is k-local if and only if, well, I can take any function on the symmetric group and turn it into a symmetric group algebra element, like so, right? I just replace it with the corresponding linear combination of permutations. Essentially, it's generating function. I hit it with this isomorphism psi. And if what I get is supported on this set of partitions where the first part has size at least n minus k, that's equivalent to being k-local. So there's this kind of algebraically intrinsic way of saying what k-local means via this fundamental result in representation theory. All right. So let's try to move on. And given this ubiquitous result, you can actually see that irreducible characters exhibit interesting locality properties. So we don't often think about characters as permutation statistics per se, but they are, right? So if lambda is a partition of n, we have this corresponding irreducible character chi lambda on the symmetric group Sn. And if lambda 1, if the first row of lambda has size at least n minus k, this irreducible character is going to be k-local, right? So that was, kind of a representation theoretic example of local statistics. So let's look at a combinatorial example. And this example is going to come from the theory of permutation patterns, right? So many of you maybe have seen permutation patterns before. We're going to be, I guess this will be a review for you, but we'll be talking about a few different increasingly complicated versions of patterns and permutations. So let's talk first about just vanilla permutation patterns. The idea is you have a little permutation V in SK, in this case 1, 3, 2. And then you have this kind of big permutation W in Sn, in this case n equals 9, and I've kind of drawn the graph. And you see within this graph, you see a little copy, right, of the red permutation inside the black permutation. So we'll say that these 3 red dots form an instance, a match, if you will, for V, 1, 3, 2, inside this larger permutation inside S9. And we're going to be interested in counting patterns. So we have a corresponding counting statistic on Sn, which just counts the number of occurrences of V. So this is not the only occurrence of V. We have others in this picture, so you'd add them all up, and that would be the value of this counting statistic. And for example, if you took V to be 2, 1, very special case, we recover the inversion statistic inv. All right, so that was one of our classical statistics, but what if we wanted some others? So what if we wanted, for example, des, right? So here we get into vincular or barred or bivincular statistics. This is not, or patterns. This is not so much my field exactly, so I get the terminology mixed up a little bit. But the basic idea is you still have a little permutation in SK and a big permutation in Sn. And now you have 2 subsets of the numbers between 1 and k. One subset A corresponding to positions and another subset B corresponding to values. And essentially, these subsets are telling you, well, which positions and which values have to come right up next to each other in the same way that indices had to be right up next to each other in des. So for example, this thing A equals 1 is saying that the first and second positions have to be the same. So these first 2 red dots are kind of right up next to each other, right, adjacent columns. And B equals 2 says that the second and third values have to be adjacent. So the second and third smallest values are in adjacent rows, right? So these conditions are called bivincular conditions. I think it's like things on positions are called vincular, things on values are called, I think, barred. And if you put them together, it's bivincular. And again, you have a corresponding counting statistic that just looks at, well, instances of V, the little permutation, occurring within the big permutation, but now you have to satisfy these kind of adjacency conditions too. And you can actually get the descent statistic in this way. That kind of motivates it. And finally, what about major index, right? So kind of the next generalization. Well, now we can have weights, right? So this is just kind of getting crazier and crazier. We can have two polynomials, right? F and G now in K variables. And now what we're going to basically do is we're going to plug the positions, right, of our pattern occurrence into F. So this first red dot, this leftmost rather red dot is in position 2. So we plug in 2 squared, and then we plug in the values to the variables in G, right? So these two red dots are at height 7 and 6. So we have 7 times 6 there. And that weight, that product, is going to be the weight of this occurrence. And we have a corresponding weighted count, which I apologize for the quintuple of indices, but I promise it will go away really soon. And you can get major index in this way because major index is a weighted descent count. Okay, so we have these weighted bivincular permutation patterns. And well, we can also think about, even more so, well, there are many instances in combinatorics where we're interested in not just one pattern, but more than one pattern. Like if you're studying, for example, smoothness and Schubert varieties, this corresponds to avoiding 2 permutations at the same time. So if I have a collection of these weighted bivincular patterns, upsilon, in sub upsilon is just the sum of the corresponding counting statistics. And if the largest pattern in upsilon has size k, then in upsilon is k local, right? So locality shows up naturally when you think about patterns and permutations. And our overall goal, and this is kind of following this terrific work of Gates and Reba, is we're going to think about these counting statistics, well, not just on the entire symmetric group, but we're going to study patterns restricted to permutations of a given cycle type lambda. And I will include a quote from a senior combinatorialist, anonymous, that is pure hell. And somehow the issue is these counting patterns, patterns and permutations have a lot to do with the matrix or one-line notation for a permutation. And that just doesn't always play so nicely with the cycle notation. So this hellish task is the one on which we will now embark together. And the way we're going to do this is we're going to replace arbitrary statistics with class functions. So let's just recall a function on the symmetric group is a class function if it's constant on conjugacy classes. And if I have any function on the symmetric group, I can turn it into a class function by applying something called the Reynolds operator. And the Reynolds operator acts on functions like this. It's a certain formula. It's replacing the value of a statistic at a given permutation with the average value over the conjugacy class of that permutation. And we can think about RF as the best possible class function approximation to the statistic F, right? And class functions, these kind of naturally come up when you restrict to cycle types, and they're going to be good news for us because we'll get to use symmetric function theory. And here's our result, pattern counting in Reynolds. So let's say you have a set of weighted bivincular patterns upsilon, and I'm going to associate a few different parameters here. So K is going to be pretty simple, the largest size of any pattern appearing in upsilon, K locality. Q, remember I had those bivincular conditions. It's basically saying what's the maximum number of bivincular conditions you could ever find, right? Biggest possible value of size of A plus size of B. And then P is going to be this weird parameter that we call power. You take the size of the pattern, you subtract off the bivincular conditions, you add up the degrees of the polynomials, you have that weird linear combination, and it turns out that parameter is actually relevant. So we have these 3 numbers, K, Q, and P, that you can read off from upsilon. And I'm going to let mi of W be the number of I cycles in a given permutation W. So here's our theorem. It says that for any positive integer d, if I look at not just in upsilon, but its dth moment, and if you're familiar with probability theory, you know that moments of random variables are very important things to look at if you want to understand distributions. So if I look at the dth moment, if I hit it with Reynolds, well, that's going to be some class function, right, on Sn. And in general, that class function, to describe it, I have to talk about, well, the number of 1 cycles in a permutation, 2 cycles, 3 cycles, 4 cycles, 5 cycles, all the way up to n cycles for arbitrary class functions, but not this time, right? You'll notice that what we get is a rational function in 1 cycles, 2 cycles, 3 cycles, and it stops at KD cycles. And KD could be much, much, much smaller than n, right? KD could be 50, n could be 1,000,000, right? So we have a rational function like this. And not only that, if we adopt this kind of strange convention where the degree of n is 1 and the degree of mi is I, the rational degree of this thing is less than or equal to d times p. So we have a rational degree bound. And not only that, if we prefer polynomials to rational functions, as well, I do at least, if we take this Reynolds thing, and if we multiply by this following factorial, n times n minus 1 down through n minus dq plus 1, then what we get is in fact a polynomial, right? So this is my theorem with Zach, kind of a very general structural property of these pattern counting statistics translated into class functions. So bit of history here. This was proven in the vanilla case, so no weights, no vincular conditions, by Gates and Reba. And a combinatorial argument of Gates and Pearson extended that from kind of a single pattern to the case of multiple, still vanilla patterns. The Gates-Reba proof is pretty cool. It actually uses algebra. It uses Jones duality, which is a version of Scherweil duality involving a double commutant relationship between the symmetric group and the partition algebra, acting on the rth tensor power of c to the n. But it's sort of unclear how to incorporate the weights and really especially these sort of bivincular conditions to sort of upgrade their proof to this setting, right? So it would be cool if you could do that. So what is sort of the proof idea? Well, somehow the idea of kind of classical science, or one of the big ideas of it, is if you have something complicated like a molecule, you want to understand it in terms of its atoms. If I understand the atoms, I understand molecules. So a k-local statistic, by definition, is a linear combination of indicator functions. So the atoms of k-local statistics are these indicator functions. And if I have a Reynolds k-local statistic, well, that's going to be a linear combination of these Reynolds indicators, right? So these Reynolds indicators are the atoms of k-local class functions, and that's what we're going to attempt to understand. And as I alluded to before, we're going to understand these really through symmetric function theory. So we have this Frobenius characteristic map, which showed up in a previous talk. And it's, well, among other things, a vector space isomorphism from the space of class functions on Sn to the space of degree n symmetric functions. And here it is written out in terms of the P basis. And we define the atomic symmetric function to be, well, you take your indicator function, you Reynolds it, you turn it into a symmetric function now. And then for reasons having to do with making formulas look nicer, you multiply by n factorial. And what does it mean to understand a symmetric function? Well, I think, like in calculus, when in doubt, take the derivative. In symmetric function theory, when in doubt, try to find the Schur expansion, right? So that's what you normally try to do, and that is the right thing to do in this case. So we'll be looking for the Schur expansion of this atomic. And, well, here's kind of one answer here. So atomic symmetric functions are indexed by partial permutations. And if I ever have a partial permutation, I have a corresponding symmetric group algebra element that just takes all genuine permutations that are compatible with my partial and adds them up, right? And if I look at the Schur expansion of the atomic, well, the coefficient of S lambda here is going to be the irreducible character chi lambda, evaluated not just on a single permutation, but linearly extended and evaluated on this whole sum, right? So this is one way of saying what the Schur expansion is. And this is, something you might be interested in if you're interested in, well, the representation theory of Sn. What are these numbers? So what's the Schur expansion? And here's an absolutely useless answer, if I can get it to appear. So I know how to find irreducible characters on permutations. It's the Murnaghan-Nakayama rule. So given this sum, you would just apply the Murnaghan-Nakayama rule n minus k factorial times. But of course, the problem with that is, well, k is usually going to be a lot less than n. This number n minus k factorial is enormous. That is not a combinatorially understandable operation. So we hope we can do better. And really, the miracle of this project, for me at least, in many ways, is that you actually can, right? So we have to think a little bit more about partial permutations to do this. So I think we all struggle mightily to teach our students in introductory abstract algebra that permutations have cycle notation and what that actually means. Well, what about partial permutations? Well, the analog of cycle notation here is still a directed graph, but now we don't just have cycles, we also have directed paths, right? So the analog of cycle notation here is this thing that, I call path and cycle notation. So here's a partial permutation on the set of numbers between 1 and 15 represented graphically. And well, the first fact is that this atomic symmetric function actually doesn't depend upon this picture per se. It only depends upon the unlabeled graph. So you can kind of work through the definitions and convince yourself of that. So we're making some progress here. Now I have dots without numbers in them. And even better, you kind of stare at these pictures and you see are there properties of the graph that tell you properties of the symmetric function. And well, our graph has two kinds of components, paths and cycles. And in fact, our atomic symmetric function factors, I guess the atom is factoring into protons and electrons or something, into something corresponding to paths and something corresponding to cycles. So even better, the thing corresponding to cycles, like this thing here, is just a power sum. So I see 1, 2 cycle and 2, 1 cycle. So I have the classical power sum P2, 2, 1. And now I have to look at this thing corresponding to paths. And this is where things get kind of cool from a symmetric function point of view. So the path power sum P mu is, well, by definition, the atomic symmetric function corresponding to a graph whose paths have sizes mu1, mu2, mu3, and so on. So we have the classical power sums, that was the cycles, and now the path power sums. So these path power sums are indexed by partitions of n. They form a basis for the space of symmetric functions, and actually they're unitriangularly related to the usual power sum basis, right? So how do we talk about the Schur expansion? Well, I'll kind of breeze through this quickly. Well, for the classical power sums, what you have is this Murnaghan-Nakayama rule that basically says you're adding up a ribbon tableau T, where the ribbons have to have certain sizes of a given shape, and you have this sign given by essentially the spin or the height of your ribbon tableau. So you have pictures that kind of look like this. But what about the path power sum? How do we find its Schur expansion? Well, now we have these new kinds of tableau that we call a monotonic, right? So monotonic ribbon tableaus. The idea is the tableau on the left is monotonic, it's good. The tableau on the right is not monotonic, it's bad. And in a monotonic ribbon tiling, well, the tails of the ribbons, those are these white dots, they have to live in distinct columns. Also, if I read these tails from left to right, their depths have to weakly decrease, they're getting shallower. And finally, if I were to add on these ribbons one at a time from left to right, what I would get at all stages has to be a partition, right? So kind of new conditions here. I hadn't seen these before, but we have these monotonic conditions. And the theorem here is that they're the right things to consider. So the path power sum expanded in the Schur basis. What's the coefficient of S lambda? If I start with the path power sum P mu, well, I have a multiplicity of mu factorial. Don't worry about that, doesn't play a big role. But now I sum up over monotonic tilings, only monotonic tilings of lambda with ribbons of size mu, same sign as before, but now I have to add the ribbons in all possible orders. So to explain what I mean by that, we have this next example where, as you can see, when applying the path Murnaghan-Nakayama rule to P321, for this single row partition, I have to add my 3 ribbons in all 3 factorial possible orders, and those all count, and they contribute the 6 here. But you'll also see that like these ribbons can never go down too far because of that monotonicity condition. Like in this example, I can never see anything after row 3, right? So this was sort of a new thing that was kind of exciting for me. And we have this result, which gives the full atomic symmetric function. So if I want to understand the Schur expansion of an atomic symmetric function, right, it's going to factor into a path power sum and a classical one, and I can understand it in terms of kind of putting these two rules next to each other, like first making a monotonic tiling and kind of augmenting it in the classical Murnaghan-Nakayama way. So two kinds of ribbon tableau that are just sort of different from one another. So this gives a formula for the action of irreducible characters on coset sums of SR contained in Sn. It proves polynomiality results, as I stated before, for pattern enumeration on conjugacy classes. And just one other little thing, I hope I won't go over too much, it actually has applications to probability theory, right? So Josh Cooper, in his PhD thesis at UCSD, defined a notion of a random sequence of permutations. So this notion of randomness comes from the idea of pattern enumeration, right? So let's say I have a sequence of permutations, W1 and S1, W2 and S2, W3 and S3, and so on. Well, what would it mean for this sequence to be quasi-random? Well, it means that if for all possible patterns V, where V is size K, I want to see V occur in my sequence about the same time as I would expect to see it, right? So the ratio of this pattern counting statistic on Wn divided by n choose k, the number of places where I kind of could see this pattern V, is going to be 1 over k factorial plus little o of 1 as n tends to infinity. And the theorem here is that, well, here are some ways you could maybe generate these quasi-random sequences of permutations. If you start with any sequence of conjugacy invariant probability distributions on Sn, and if you let sigma n be a random permutation distributed according to this distribution, if this condition is satisfied, and this is basically saying that you're not allowed to have too many 1 cycles, right? The expected number of 1 cycles in any permutation in Sn is 1, right? And that's going to be a whole lot less than n, but as long as the number of 1 cycles in your distribution basically gets pretty far away from n as n grows, then this sequence is quasi-random. So you might imagine dependence that's a lot more complicated on like 2 cycles, 3 cycles, 4 cycles, but this is somehow saying 1 cycles are the only ones that actually matter. And with that, I would like to thank everyone very much for listening.